Good morning, mathematicians. What are we going to talk about today? I think I'm back on my D module BS. I think so. I think I'm going to compute some stuff, but we'll see. Maybe you guys have questions. Maybe you guys will finally tell me about things you've been proving. And we'll talk about that. Or not. Who knows? Good morning, Yaman. Good morning. So let's see. One of the things I want to go back to one of these computations I was talking about with D modules. Basically, here's what I want to do. I want to look at this example again, where, so we've got the complex numbers, and I have the D module, which is just given by taking the left ideal of x, and for the inclusion of the origin into the complex numbers. Finally sent some emails to professors asking for letters of recommendation. I hope you hear back. I probably should be emailing some more people asking about what postdoc opportunities are out there. So what is it that I want to verify? Yes. I want to examine the behavior of the derived pullback of this D module to the point. So I want to see what happens here. Did I see the new Gates-Gorey-Raskin paper? I did indeed. I think we brought it up on stream yesterday. Not that I understand a ton of it, or any of it. But yeah. One of these days. I printed off some stuff, some infinity category stuff, so maybe I'll better understand the statement soon. I mean, they make sense on some level, but yeah. Okay, so what is this? Well, first we need to talk about the derived pullback. So let's take a look. Let's take a look there. Although I guess there isn't much to say, right? It simply is the derived pullback. Mind you, I'm hoping that somewhere in this book there will be a nice formula for this case of pulling back to a point, but so far it does not appear to me as if that's the case. I thought it would be, though, because there's a lot of nice formulas for closed embeddings. Okay, but it does look like there's something of a recipe how to build this. You shouldn't really need any infinity category theory to understand the statements. Just pretend they're fancy one categories. That's true. It is true. I guess one can just sort of read it and essentially just pretend they're all regular categories of sheaves on spaces, and should all make sense. Hello, Padraig. Hello. Canonical isomorphism. Does that actually help me compute this thing, though? I mean, I guess it gives me a resolution, right? I mean, I guess this... Okay, this tells me a way how to represent the complex for a closed embedding. So, yeah, I guess this is a place to start then. Smooth morphism between smooth algebraic varieties. That is not the case that I'm in. Is this my research? Yeah, this is, well, the things I'm currently working on, the papers I'm currently working on don't really deal with D modules, but this is things I'm trying to learn about so that maybe the next papers will employ some of these D module techniques. That's the idea. So, yes, I mean, yes, essentially. Using a flat resolution of M, but M is a D module. So I have no experience of what resolutions of D modules tend to look like. Yeah. A flat resolution of M. Yeah, so one needs to begin with a flat resolution of M. Ugh, and then take the derived tensor product. Yeah, this computation just doesn't seem easy. This doesn't seem easy. I was told D modules are supposed to be easier to work with, you know. And I'm not sure how true that is. I mean, I guess it should be equivalent to just a module over the Weil algebra. In which case, you know, just one could apply more standard techniques of producing resolutions. But, okay, let's see. Let's see if there's something nice here in the case of a point. Note that this, if f, if f is a closed embedding, the dimension of x less than the dimension of y, yes, then this D module is locally free of infinite rank. Oh, what? Does not necessarily send this to this? Wait, f is going from x to y? No, pull back. Okay. I mean, that's a little bit concerning. Okay. Oh, maybe that's why we need the shift? Right. Yes, we do need that. I do need to compute that shift. How's everyone doing? What have you guys been proving? You guys never tell me what you've been proving. Why is K naught X for X compact Hausdorff useful? What's an example 1.3.2? That's a good question. 1.3.2. Yeah, this is just the underived version, but yeah. So for your question, why is K naught of compact Hausdorff useful? I mean, I'm not sure that. I'm not sure that. Yeah, I mean, I don't think there's anything in particular that X being compact Hausdorff makes that useful. Rather, K naught in general is useful. It's just an invariant of a space, much like anything, right? Well, how do you tell apart two topological spaces? Well, you could have two topological spaces with the same number of holes in them that are different, but if they have a different number of holes, then you know that they must be different, right? So same thing with K naught. It's just some invariant that can, but not always, help you tell apart two spaces. So it's that K naught is useful, right? Not that K naught for X compact Hausdorff is useful. Now, if X is a compact, I mean, compact spaces are also just nicer, right? There's just more we can say about them. They're just better behaved. So, and same thing with Hausdorff spaces. So, yeah, the thing is, K naught is what's useful. And then probably you're asking this question because you see a bunch of stuff about computing K naught of compact Hausdorff. Well, it's just that that's a case that is easier for us to work out. Trying to prove crystalline and symptomic cohomology. Stuff about that. I don't know. I've never. I've heard of crystalline, but I don't really know what it means. I've definitely never even heard of symptomic cohomology. Good morning, good morning, good morning, Ken. Yeah, so this is just the case. This is just the underived case for a closed embedding. Yeah, I'm not sure. So let's go back. Where were we? 1.5 point something. Closed embedding. Da da da. Da da da. Still looking for something that will make my life easier with these computations. Do I think every professional mathematician should have a basic understanding of algebraic geometry? Nope. Absolutely not. Absolutely not. That doesn't make any sense. I mean, I'm heavily biased towards algebraic geometry, but no. I mean, if your life's work is to solve differential equations, or yeah, I just don't see why that would be a good use of a professional mathematician's time. Who's imagine you're using I don't know, yeah, differential equations for some like military application or something. Probably not worth your time, right? Unless, I don't know, maybe like Grosvenor bases come up somehow. In which case, I think you could just pick that up on the fly. In the beginning of Vakil's book, there is exercise 1.4G where they ask to construct a groupification functor, but you're unsure how to show a jointness when the semigroups are not unital. Well, let's take a look. The rising C textbook. I still need to buy myself the hard copy. You're probably just confused, but maybe you could look at that. Yeah, let's take a look. 1.4G. Let's see. Oh, it's going to take a while to search through 850 pages. I guess I could just scroll there. 1.4, boom. (1.4G), constructing the groupification from non-empty abelian semigroups, to abelian groups. Show that H is left adjoint to F. Okay. And they even give us the general idea for experts. We have a full subcategory of a category. We want to project from the category to the subcategory. We have this automatically. Well, I don't know about that. I'm not that adept at category theory, but okay, yeah. So we've got this groupification. We just put this equivalence relation here. Yeah. So what's the best way? What's the best way to prove this? So okay. So we've got. Wait again. Let's. What are our categories here? Non-abelian, or sorry, non-empty abelian semigroups. So I don't know. Ab S, I guess we'll call it. Ab S to abelian groups of its groupification. Yeah. Ab S to ab. And, right, so we'll send some semigroup to HS, and then conversely, we'll send some abelian group to the forgetful functor. And we want to, wait, which ones? H is the left adjoint. So H is the left adjoint, so we want to provide a natural isomorphism here. Yeah. Okay. ABS is like a six-pack cat. It's too early. I don't get it. Actually, it's not that early here. It's 9:22. You're happy for your summer to study fun things, but then you're told to study for quals, so it's been a boring summer. Yeah. Well, I don't know. As someone asked yesterday on their advice, like, enjoy it. You might miss it, actually. You might miss it. Believe it or not. So try and enjoy studying for quals. Tired of studying for algebra, quals, and finite group theory. So boring. Wow, blasphemy. That is blasphemy on this channel, Ken. Compared to lots of other stuff, I mean, sure, I guess. I don't know. I mean, I'm one of the people I'm tutoring at the moment. We're going through some like classical equation stuff and the CELO theorems, and I don't know. I always have fun revisiting those things myself personally. Yeah. So okay. And let's see. What was this question? They asked to construct groupification, unsure how to show adjointness when the semigroups are not unidal. I see. And they're not assumed to be unidal? Yeah, what does it mean to be a semigroup? What does it mean to be a semigroup? Just that you have the binary operation that's associative? Associative binary operation, right. Not necessarily unital. Okay. Well, there's different ways we could go. We could construct the unit and co-unit of adjunctions. Or we could try and just directly describe this map here. Right. So I don't know what's easiest. But okay. Let's just power ahead naively, I guess. So suppose that we have an abelian group homomorphism from HS into A. I don't know, what am I going to call this? I'll call this big phi SA. And okay, let's see. You've tried to go from S to HS by simply applying C dot B. Tried to go from S to HS. I'm not totally sure I understand what you've written there. Yeah, I don't know what I'm not sure I understand all your notation there. G is the abelian group. The question, Boris, is we're trying to show that these are adjoint. So H is the groupification functor from commutative semigroups. Yeah. And then this is the forgetful functor from abelian groups. Shouldn't this just be the identity in one direction? I think it should just be the identity in one direction. That's true. Yeah. I mean, right. So if phi is defined here, then, right. I mean, basically this tells us how to define it on, we can define a map. So, capital phi SA of little phi, defined on S, some element of the semigroup. We can define this to be, well, this is going to be like equivalence classes. HS is going to be equivalence classes of pairs, right? So, so phi S0 would be my guess to make this a well-defined homomorphism. Proof by it looks obvious. Yeah, actually, I should probably just employ that method so that I could get like 20 more papers out by September. Right, so probably I would just define the map like this. Surely this should work and be a well-defined homomorphism. Yeah, is it well-defined? Let me just quickly... I mean, surely it must be, because it's the first thing I wrote down. And natural transformations are always the first thing you write down. But, okay, if S0 is equal to T0, then what does that mean? That means that S plus E is equal to T plus E for some E and S, right? Is that our equivalence relation? Yes. Wait. Yes. So S plus E is equal to B plus E. Right, and then that implies that phi s plus phi e is phi t plus phi e. Or wait, sorry, phi. What am I saying? What's 0 in this case? Oh, right. Sorry. Aha. Okay. Right. So what should I be doing if there's not a unit? This is weird. Is this graduate level? Yeah, I would say that this is graduate level. Right, not unital. So, huh. How would we define this map then? Oh, it could be, yeah, it could be there's a typo. How do we define this map? S plus S? Oh, nice. Nice suggestion, Padraig. Nice. Yeah. Okay. Very nice. Yeah, S plus S. S plus S, S. Nice. Okay. Yeah. And then, right, to see it's well defined, if we go S plus S, S is equal to T plus T, T. Well, wait a second. It is well defined because you can just say, right, it is well defined because we're putting as input S and then we're just gonna like spit this out. So yeah, it should be fine. Nice. Okay. And then I guess I want to explicitly define the inverse, right? So psi, if I let psi be the inverse, so phi will go this way, psi will go this way, capital psi will go this way. And yeah, if we suppose that we have an abelian group, or sorry, just a semi-group morphism, baby psi. Now I need to beef it up. I need to say what it's going to do on pairs. And I mean, probably my guess would just be if we, so psi takes us from S into, so we just go psi S. Now that sits in A, I mean, sort of forgetfully, but then we can remember that we have our thing in A, and since it's, we're supposed to think as ST as S minus T, probably if we define it to be that. So this would be my guess, actually. This is my guess that these are our two inverse natural transformations defining the adjunction. I don't think S0 was correct though, because there is no 0. Right? These semigroups are not assumed to be unital. So 0 doesn't make sense. S into GS is a monomorphism, and you compose with that. Sure. Now we don't know if S plus S is non-zero. I don't know what that means. So is that I don't think that's an issue, is it? Yeah. So this is my guess. This is my guess. It should be this. Yeah, SS should be, well, yes, SS should be 0. That's true. That's absolutely true. In the groupification. Yeah. So I don't know, Jonas, if this is enough to answer your question. I mean, now all the hard work needs to be done. I don't know if you want me to do all the hard work too now. These are that, and now everything else is just routine, right? You just need to show that both of these are homomorphisms in the appropriate sense, and that these are inverses to each other. And then you need to show naturality. So it might actually be easier to provide the units and co-units in this case. I don't know. It's always the same amount of work in the end, usually. How do we prove the relation is an equivalence relation without unidal assumption? I don't think that's that hard, right? So what's the relation? It says that ST is related to AB if and only if there exists an E in S such that S plus B is S plus B plus E is A plus T plus E. How do we find the stereographic projection map to the sphere? So maybe we could talk about that in a second. Let me just say something about this equivalence relation. You're afraid to ask what's the functor for anything of lesser structure than a group? Well, you shouldn't be. This is a good exercise for you, Dason. Okay, so let's see. I see, because now the question is STT. Oh yeah, so to prove it's reflexive, yeah, we just need to provide, we just need to demonstrate an E. So just, I don't know, you literally pick anything, right? So S plus, oh no, wait, we can't pick anything. Wait, I'm so confused. Right, it should be S plus S equal to plus E is equal to T plus T plus E. Is that true? Did I do this correctly? Right. No, S plus T. Okay, great. Yes. So, right. So we need to provide an E such that S plus T plus E is S plus T plus E, but literally pick anything. So I don't know, pick S. And therefore we've verified the condition. So yeah, it's reflexive. And then, okay, symmetric, again, is basically the same thing, right? Because we've assumed that it's an abelian semigroup. So we just need S plus T is T plus S. And we need to, again, just put S here. And yeah, those are, in fact, equal because it's an abelian semigroup and associativity and blah, blah, blah. Yeah, and then I don't remember who asked the question, but probably this is enough for you to see the rest. Work out transitivity for yourself, which is always the hardest case. To be fair, it's always transitivity, associativity. Those are always the hardest ones. Yeah, Jay. As for your question, I don't know. It just seems to generally be the case. Free, whenever you have a forgetful functor, it has a free adjoint and vice versa. I don't know if there's a concrete way to say this. Maybe there is some way, pun intended, with concrete. Like maybe you can say something about, if you have a category with some nice forgetful functor to set or something, maybe there's like a general principle. I don't know if there's a general theorem, but it definitely just seems to be true all the time. Oh, hey, Jeff. Or Jeffrey. I should ask. Sometimes I write Jeff in our notes, and I don't know if you prefer, if you don't like being called Jeff as short, or just Jeffrey. So let me know if you mind or if you don't care. What about that book, The Rising Sea? Yeah, what about it? What about it? Go. You should buy the hard copy. I should buy the hard copy. It's a good book. Magma should be the set of labeled binary trees. Interesting. Yeah, how to project. Right. Yeah, Alex. So I'll talk about this a little bit, and then well, let me tell you. I'm probably going to go fairly soon. I'm not going to go through the whole thing in detail, but let me tell you the steps you should take in order to do this. So what my recommendation would be before trying the full stereographic projection in 3 dimensions, I would begin with just taking a 2-dimensional slice. So I would do something like just take let this be, say, the z-axis, and let this be the y-axis. Actually, let me redraw that a little bit. So I would start here, right? For any math problem, I mean, this is what I'm telling my students a lot in discrete math. And, they're like, oh, there's some problem with like some set of 8 elements, and you need to count the subsets of all things that like don't intersect some set of 4 elements. I'm always like, they give you some question, but try and write down an easier version for yourself first, and that will help you understand what's going on, right? So I would start off, imagine, if you forgive this terrible circle, just look at the cross section, right? And then later you can add in the y-axis, but I would just get down the formula for the cross section first, right? So and mind you, I should also ask, it depends on what kind of stereographic projection you're doing, right? Because there's one where you have the XY plane intersecting the hemisphere, but then there's also I don't know which one you're working with, because then there's also the one where we put the sphere just above the XY plane. So does the forgetful functor from top to set have an adjoint? Yes. In fact, there are 2. It has both a left and right adjoint. One is the discrete topology, the other is the indiscrete topology. This is one of my favorite, as Arad said. Oh, co-discrete. I've never heard it called co-discrete, but that, makes sense. This is one of my favorite examples of discrete things. So yeah, I don't know, Alex. I don't know which of these 2 pictures you're working with. Actually, I think for stereographic projection, it has to be the second picture, actually. Yeah. So here's what I would do, right? So we've got our z and our x axis here, and I would just try to circle centered at 0, 0. Centered at 0, 0. Right. Okay. Oh no. So it doesn't have to be this one. Okay, we're doing this one. Okay, we're doing this one. So I would just start with a simple picture like this, right? Work it out in this simple 2D case first, where you're taking the slice of the XZ plane, right? So you want to go back and forth between these between these coordinates, right? So some point on the, mind you, okay, wait, I've drawn this picture a little stupidly. So let me make it slightly less stupid. Let me try and make a more good or better sphere like this. And then I guess we'll pick this point here and we'll go like that, right? So, yeah, so we want to talk about how to go back and forth between these, right? So this will have some coordinate r theta that we want to try and determine, right? So this will be r, and this is going to be theta. And we want to determine what the point is here, x, y, that it gets projected to on the xy plane. Or, I mean, maybe you don't necessarily need to use r theta, right? So, like, maybe you want that in Cartesian coordinates as well. Of course, we know exactly how to translate between these two things. It's the bane of your existence how initial and final topologies are opposite of their universal properties. Huh. Whoa. Okay, so yeah, where do we even begin? I mean, I guess we just got to try and draw as many triangles as possible, and play some games to figure it out. So I guess which way should we go first is the question. Maybe we could go from the coordinates of xy to the coordinates of r theta. So, well, we know that we also have some side lengths. We know that both of these lengths are 1. And so we want to go from xy. And we also know that r is 1 too, by the way. So actually, all we need to determine is theta. This stuff's popping off in chat. Con extensions, inverse limit. I mean, I do always get confused with like left, right, and which is inverse limit, direct limit, blah, blah, blah. Like, I know the ones I mean, I can use them correctly in those contexts, but I always mess up what's left, what's right, blah, blah, blah. Okay, I remember actually I made a student go through this last semester in my mentorship program, and there was an easy way to do it. I look at it immediately. I'm tempted to try and do some sort of I'm tempted. Oh wait, I wrote some nonsense here. That's not one. This is 1, and then the whole thing is x. And actually, wait, what am I even doing? This is just a single number. What am I doing? This is just a single number on the x-axis, right? Yeah. So this is x0 really in coordinates. Yeah. And so the length of this over here of this red part is going to be the root of x squared plus 1. And we've got we should be able to work out all of the angles, right? We just need theta. Can I talk a bit about universal properties and slice categories and initial objects? Maybe tomorrow. I wasn't planning to be here this long, but I do want to try and give Alex enough to get started working this out. I'm just trying to remember. There's a simple way to do this. I could have made more progress already if I had just used like the more uglier sine laws. But I remember there's some trick to this. If we use the similarity of triangles somehow, like this angle, I don't know, call it phi. Well, if we look at this is a similar triangle to here, right? And so this is here, and then this is alpha. So then this one also has to be alpha. I guess we want to try and find the height of this point here. Why is this hard? Why don't we just parameterize the line and find when it intersects y equals -1? I don't know what you mean by that. I'm not exactly sure what you mean by that. Wow, this is like very simple geometry. And, it's so funny. I literally went through this with a student like 2 months ago, and I already forget what the trick was. I think this was part of it, because yeah, I know there's some trick using the similarity here. Weird. Well, yeah, I don't know. I don't know. I mean, this is like pi minus theta, right? Or pi over 2 minus theta over here. So that should tell us what this angle is as well. We'll call it beta. But then beta, is that similar to something else? I mean, whatever angle is here, gamma, we should have alpha plus beta plus gamma being pi. We know that the length is sine theta, which gives the length ratio. The length of what? The length of what? Oh yeah, somehow, right. I guess we could use right. Somehow we want to use the length ratios. Right. So yes, right. That's what it is. So we want, if I wanted to get the y coordinate of this point, I know, what do I know? Right. So I can use some of the ratios here. So the ratio of, say, 1 to x from the big triangle should be the ratio. So I don't know, I'll call this, I called it x, but really I want, like, let's say the x naught, z naught. So then that should be the ratio of z naught to, but we don't know this x distance here. We don't know what that x distance is. No, we don't have enough sides to term down here. What the hell? This is like basic high school. I can't do it. 1 minus sine theta, 1 over x is 1 minus sine theta. I don't see why that's the case. I don't see why that's the case. Wow, how many people hanging out in advanced math office hours does it take to do basic trigonometry? But this is the right idea. We do somehow we want to use a similarity of lengths here. Right. I think we need. I don't know. Maybe I need to play more of these angle games here. Right. What else do we have? We know that. Well, we also know that alpha plus beta plus pi minus theta. Right. Those are the things of this triangle. So that needs to add up to pi, and so that would imply that gamma is pi minus theta. I guess we knew that already. So so alpha though. Alpha, we know that like cos alpha is 1 over this thing. So we can determine alpha. We're trying to figure out the y coordinate of this point here. Right. So we have this angle, but we don't have any of the distances of this thing. Oh, right. But we do also know, we do also have like sine alpha over 1 is, should be equal to sine phi over, okay. Yeah. So, okay, we have the distance to here. The distance to here is x. So, so sine phi over its opposite in the big triangle, which is 1, should be equal to sine alpha over its opposite in the big triangle, which is x. Just parameterize the line. Is that really the solution? I mean, I don't remember ever working this out by just parameterizing the line. But this does at least tell us how to relate alpha and phi. And if I have alpha, what the hell? Okay. Oh my God, it's 10 o'clock. I need to get to work. It's time to cheat. Huh? Oh, what the hell? Google. No, this is the better. This is the way I did it is the better way to do it. Yeah. But this just tells the formulas. I wanna know how do I get it. Eh. The line is that. I see. Maybe it is better to do the line. Well, I guess we'll leave it there. My inability to do basic high school geometry forever immortalized on YouTube. Who knows what we'll do tomorrow? What did someone ask me to do tomorrow? They wanted me to talk about universal properties. Maybe we'll talk about universal properties and slice categories tomorrow. Until then, see if you can outdo me on stereographic projection. Yeah.